Hi guys, and welcome back to my channel. In this video we'll be going over the energetics of ionic bond formation. So basically we'll be talking about, right, why does, say, if we have Na, right, and Cl minus, why does this ionic bond sort of form, right? We have this sort of notion of lattice energies that we've talked about in AP Chem that sort of brings these two together. Why is the potential energy, lower, right? And to what extent is the potential energy lower when you have, ions separated and ions together? And why does this form? Why is it energetically favorable, right? It's similar idea to covalent bonds. Like why do we have bonds between atoms? Why don't atoms just sort of be apart on their own? These bonds lower the potential energy. And we're going to talk about the energetics of ionic bond formation in this video. This is the first of the chapter 2 lecture videos for Atkins, and let's just get right into it. Okay, so first I want to talk about the Born-Haber cycle. So this is a very, very important cycle that's used to solve for lattice energies. So what exactly is lattice energy? I've defined it right here. It's the difference in energy between the ions packed together in a solid and the ions separated in the gas phase. So basically, say we have Na, let's again take the example of Na plus and Cl minus, and say we've basically overcome the lattice energy. What does that mean? These guys are like floating around in the gas phase and they're all separated from each other. We know that this is like a high potential energy, right? Because positive and negative charges like to come together. They like to sort of, because they're attracted to one another, right? These positive and negative charges are attracted to one another, and they don't like to be separated. They don't like to be in the gas phase. Instead, they like to be really close together, not roaming around fast. They like to be close together. They like to be attracted to one another. They like to be, next to each other. So this is a high energy state, right? When we have them in the gas phase, whereas what we normally think of as something like table salt, right, NaCl, we have these sodium and chlorides, tightly packed together in this sort of, I'm not drawing it accurately, of course, but like they're tightly packed together in this sort of solid, in this crystalline structure, where these pluses and minuses are together, right? The pluses and minuses are attracted to one another, and the potential energy is low because the pluses and minuses are next to each other, right? They're close in their distance. So because of that, we can think of this lattice energy, right? It's how much energy we need to overcome this sort of attraction and make the ions just be separated in the gas phase. So how can we solve for lattice energy? Remember that Hess's law is basically tells you that if you add two reactions, you can add the enthalpies, and that'll be the enthalpy of the final reaction, right? So basically that's the entire concept we're going to use to solve for the lattice energy. And this diagram, I think, shows it really, really well, this diagram to the right. And I'll just sort of explain what it's showing, right? So let's start with our NaCl at the bottom. We can see that this low energy state, that's our NaCl as a solid, right? And you can see our first step, how do we get to Na as a solid and half Cl2? You might notice that this sort of Na solid plus half Cl2 going to NaCl is something called the delta H of formation, right? It's the delta HF. The delta H of formation is basically how can we make our final product using the elemental forms of the atoms in our final product, right? So when we're making NaCl, it's basically saying we start with our solid sodium, which is the elemental form of sodium. We start with our gaseous chloride, which is our gaseous chlorine, which is our elemental form of chlorine. And we react that to form NaCl, and that delta H is called the delta H of formation. And you can see that written here, right? This delta H formation is negative 411 kilojoules. So if I wanted to go the other way, right, if I drew my arrow the other way, if I flipped my reaction around, this would be plus 411 kilojoules. The next thing we have is sublimation. So you see delta H sublimation of Na, of sodium. We want to make the sodium a gas. And you can see that that takes a certain amount of energy. And now we have our sodium and our chlorine in the gas phase. Now we look at the next thing, we take the ionization energy of sodium, right? The ionization energy is how much energy does it take to pluck an electron away from sodium, right? So basically what I'm doing is I'm removing that electron, the valence electron from sodium. That takes a certain amount of energy, and we end with this Na plus ion in the gas phase. And we still have our chlorine gas, right? Because we haven't done anything with that. And finally, or not finally, but the next thing we do is we atomize our chlorine. What does atomize mean? That means we basically break the bond between the chlorine and we make it into the atoms, right? So we go from half Cl2 to one of just Cl. And this takes a certain amount of energy because you have to break the bond between the chlorines. That's called the delta H atom, subatom, right? We have delta H atomization of chlorine. That takes energy because you're breaking that bond between the chlorines. And here we have 122 kilojoules. Now we see that at our highest energy state, we have sodium as an ion in the gas phase, chlorine not as an ion in the gas phase. So next, we want to make sodium an ion in the gas phase and chlorine an ion in the gas phase, right? Because when we're thinking about lattice energy, we want to compare relative to this NaCl what the energy of the sodium and chlorine in the gas phase is, because that's the ion separated in the gas phase. So how can we go from Cl in the gas phase to Cl minus in the gas phase? We need to look at the electron affinity. The electron affinity is what is the enthalpy such that when I just shove an electron into a chlorine, right? What is the enthalpy change? So my electron affinity is negative, right? You can see that it's negative 349 kilojoules. And that electron affinity basically adds an electron to the chlorine in the gas phase. So you go from Cl in the gas phase to Cl minus in the gas phase. And now we have Na plus and Cl minus in the gas phase, and we can compare this relative to our original NaCl as a solid, right? So this difference in energy levels here, this difference in energy level is our lattice energy of NaCl. So you can see all these things we used, right? Let's just go over it. We used our delta H of formation. We used how much energy it takes to sublimate something because we need to make these things into the gas phase. We used ionization energies because we need to take an atom and make it an ion because we want to compare ions in the gas phase to ions in the solid phase. We used atomization energies because chlorine exists as Cl2 in its elemental form, but when we want to compare to for lattice energy, we don't want Cl2, we want just Cl, and eventually we want Cl minus, right? Because we want the ion in the gas phase. So we used the atomization energy, then we used electron affinity, and electron affinity took us from our Cl to our Cl minus. And finally, now we have Na plus and Cl minus, and that's exactly what we want. And then we can compare our energy of that to the original energy we started with. So hopefully this cycle kind of made sense. And this is, a really, really useful way to solve for lattice energies. And all it is an application of Hess's law, an application of adding enthalpies to get something you might think you don't originally have, right? You might think, oh, we don't have this lattice energy. But with all this other information, you can figure out the lattice energy using just the fact that our enthalpy is a state function, which is a really nice property. So now I just want to talk a little bit about potential energies of lattices, and we'll actually do a derivation in the next video on how we can sort of see how this equation comes about. But in this video, I just want to introduce this equation and show you like key features of this equation. So we have our potential energy, E potential, is equal to negative A. A is called the Madelung constant, and this is a very important constant that depends not on the ions in the crystal or in the lattice, but only on the crystal structure. So this is kind of a pretty cool thing, right? We have this constant, sorry, we have this constant only depending, so this A value only depends, I want to stress this, right, only depends on our crystal structure and not the ions in the crystal structure. So say we have, say we have NaCl and NaBr, and they have the same crystal structure, or NaCl and AgF, and they have the same exact crystal structure. That means their A's are going to be the same. So this is just sort of an interesting thing I wanted to bring up, and a thing to remember, that the A value does not depend on the ions that are in the structure, just the structure itself. And you can see that there's these different structures, and we'll eventually get to talking about these structures, but you can see that based on the different structural types, we have different values of A. So we have rock salt, fluorite, cesium chloride, all of these different structures have different A values. Okay, so we can see that's sort of like a constant, that's sort of like a proportionality constant. You can see it sort of in the front. It's like a little bit looks like a proportionality constant, just a constant multiple of some more complex equation, right? And let's look at what that complex equation is sort of saying, right? You can see that we have 1 over 4 pi epsilon naught times, if we take the Na out, let me take the Na out, that's just moles, right? That's just Avogadro's number, which means that we're basically multiplying this so we get an energy per mole, right? This is basically helping us get energy per mole rather than energy per ion. So that's sort of where Na comes in. If we look at it without the Na, we should get energy per ion, right? And maybe that'll make more sense to look at first. So if we rewrite this, we get Z1, Z2 times E squared over RD, right? And we look at this, and we've sort of seen this before. This is actually the equation for potential energy in general, right? Our equation for potential energy is equal to K times Q1, Q2 over R. R is our distance, so D is basically R. Q1 is the charge of one thing. So if we look at the cation, for example, if Z is plus 1, so if Z1 is plus 1, if our charge on the cation is plus 1, that actually means that the charge itself, it's just devoid of one electron, right? Which means that we're basically saying that we're doing 1 times E, where E is our charge of an electron. So the actual Q1 is E, right? Because it's just devoid of one electron. A plus 1 charge just means lost an electron. So we have K times Z1E, because Z1 is our multiple, how many electrons we lost, times Z2E, right? This would be how many electrons we gained, because for our anion, right, say Z2 is -1. Say we have a -1 charge. That basically means that we've gained 1 electron, so this charge will be negative. And then divide by our D, right? And K is 1 over 4 pi epsilon naught. K is just 1 over 4 pi epsilon naught. That's our Coulomb's constant. And this is our equation for potential energy. And you can see this looks awfully similar, right? Because if we multiply this out on the numerator, we get Z1, Z2, and we also get E squared. So this looks really, really similar to our potential energy of our lattice, right? So I just wanted to give you a little intuition for that. We'll actually derive this equation in the next video, but I just wanted to show you that this is very, very similar to what we already know is the equation for potential energy. Okay, so yeah, that's what I wanted to talk about for potential energy of lattices. Let me go to the next slide now. So let's talk about the Born-Mayer equation. So we talked about the other equation for potential energy of lattices, right? And you might have noticed that as D approaches 0, the potential energy gets more and more negative in the previous equation. This is very, very important, right? Because this is wrong. So if we remember the previous expression, it looks something like we had our our potential energy was proportional to negative 1 over d, basically, because the charges and everything were constant. They're all constant. So as our d goes to 0, we have that our potential energy will go to negative infinity, right, for our previous expression. But we know that when potential energy lowers, when we have more negative potential energy, that means our compound is more stable. So this basically, so you might ask the question, right? Why doesn't all the ions sort of just collapse to a point, right? If it's more stable as our distance becomes smaller and smaller and smaller, why doesn't our ions just sit right on top of each other? Why is there even a distance between the ions? And that's a good question. That's what we answer with the Born-Mayer equation, right? That it doesn't make sense for the ions to just sit on top of each other. And that's because we have repulsive effects. There's repulsive effects from the nuclei. Think about when two atoms or two ions get closer and closer together, their nuclei also get closer and closer together. And the nuclei is just a huge sort of concentrated positive charge. And when these concentrated positive charges get close together, what is going to happen? There's going to be this huge repulsion, right? Positive charges don't like to get close to each other. So repulsive effects from the nuclei stop the collection of ions from collapsing to a point. Basically, D equals 0 is not the lowest energy state. So let me write that. D equals 0, not lowest energy state. And this is because due to what? Due to repulsion of nuclei, right? The nuclei are going to repel each other. So that's an important concept. So now let's look at the Born-Mayer equation and see how that actually fixes it, right? There must be a certain distance such that distance is not equal to 0, such that the potential energy is minimized. Sorry, that should be minimized. And that's because, right, because as D gets closer to 0, we should have repulsive effects factoring in, and the ions will not collapse to a point because the nuclei will repel each other really, really highly, right? They're going to repel each other a lot. So there must be some sweet spot, right? If they're too far away, the ions aren't attracted to each other. It's not low potential energy. If they're too close together, there's huge repulsions. Again, that's not low potential energy. There's got to be a sweet spot, right? There's got to be some D not equal to 0 such that the potential energy is at a minimum. So let's look at the Born-Mayer equation and see what that says. So we can see this graph, right? This graph to the right might be easier for visualization purposes. We have our total potential energy here on our y-axis and the D on the x-axis. So you can see as our D gets farther and farther apart, right? As our D increases, we have our potential energy sort of approaching 0. So as D approaches infinity, we have our potential energy U approaching 0. That's because when our distance between the ions are farther and farther apart, there's basically no interaction between the ions when you pull them all the way apart, when you make D really, really large. There's no interaction. And what happens when there's no interaction? There's basically 0 potential energy. There's no stabilizing and there's nothing repelling, right? Because there's just no interaction. So when D approaches infinity, our potential energy goes to 0. But also we have when D approaches 0, our potential energy goes to infinity, right? We have this, why? We have this because as D approaches 0, we have huge repulsive effects from our nuclei, and as our positive charges in the nuclei get closer and closer together, the potential energy goes up and up and up, and eventually, approaches infinity. So that's why our curve looks this way. And you can see right in the middle, or not right in the middle, but somewhere in the middle, we have the sweet spot where we have our potential minimized, and that's at this value of D, right? So let's look at the actual equation. We have E of the potential energy at the minimum, right, is equal to negative A. So we can see that everything looks exactly the same, right? This part is exactly the same. Let me note that. Exactly the same as our previous slide, right? It's the same exact equation. We have our Madelung constant, we have our Z1, Z2, E squared, and we have our Avogadro's number, and we have the inversely proportional to D. But again, you see here that there's another factor, 1 minus D star over D. So let's see what exactly this does in relation to our potential energy. If D is less than D star, what happens? So let's first, when we look at the left part of this equation, right, that we said was the same, we have to note that this is always negative. How is this always negative? Our Z1, Z2 absolute value is positive, E squared is positive, 4 pi epsilon naught is positive, distance is positive, Avogadro's number is positive, this A is positive. So everything is positive, and then we have a negative sign out front, which means that that part has to be negative, right? We have a negative potential energy in that part. Now let's look at this other part and see what happens when D is less than D star, right? If D is less than D star, that means D star over D. What does that mean about D star over D, right? That means this is greater than 1 if D is less than D star. So what that means is that 1 minus D star over D is going to be less than 1. I mean less than 0, right? Because D star over D is greater than 1, so if I do 1 minus something greater than 1, I'm going to get something that's negative. So then I'm going to have a negative number times another negative number. That's going to give me a net positive, right? A net positive potential energy. So this is important. If D is less than D star, this means ions are very close together, right? Ions are very close together. Nuclei repulsions become significant, right? And when nuclei repulsions are significant, we have that the potential energy should increase. And we see that with this equation because our potential energy is greater than 0, right? It's positive because we have a negative term multiplied by another negative term. So we can see based on this equation, right, it tells us, it fixes the original problem we were having. It says that as our D becomes really small, as our D becomes much smaller than D star, we end up having really, really high potential energies, which makes sense because the nuclei are repelling each other, it's not happy, therefore it's a high potential energy. Okay, so that's basically what I wanted to cover in this video. Thank you guys so much for watching. I hope you learned something, and I'll see you in the next one.